Okay, so welcome back. So today, let me begin by showing you the final presentation. And if there's any error, please let me know. Then I'll go into this week's topic. Okay, so we have 7 groups that will be present after the Thanksgiving break. Group 1 is the subject that they choose, entanglement-based machine learning on a quantum computer. I hope this is correct. I was using the discussion board that you guys posted, and if there's ambiguity, I use the homework that you posted. Group 2 is on universal blind quantum computation, and there are 3 references they cited. Group 3 is on can the wave function collapse algorithm run on an actual quantum computer. Okay. Group 3 is on unpaired Majorana fermion in quantum wire. This is based on a paper by Alexei Kitaev here. Group 5, I think it's on Google's paper on quantum supremacy. And group 6 is on hybrid quantum algorithm to classify Hermitian matrix definiteness. Group 7 is on quantum internet. Okay, I hope this is the correct description. If there's any error, please let me know. And each presentation is about 20 minutes plus 5 minutes question and answer session. And so there will be 3 groups on the first day and 3 groups on the second day, and there's only 1 group. I think that's group 3 on the last day. Okay. Any question on presentation? You should prepare the slides, and I estimate probably around 15 slides. No, probably no more than 20 slides because you only have 20 minutes. Okay. If there's no further question on presentation, let me go to this week's topic, which I call quantum matrix. So it's about quantum simulation and sensing and metrology. Okay. So to talk about the early idea of quantum simulations, probably this person stands out, which is Feynman. Quite early in 1959, he gave a talk at APS meeting, and he mentioned atoms behave on a large scale. Nothing like the atoms on a small scale behave nothing like on a large scale, not like an everyday object, okay? Because they satisfy the laws of quantum mechanics. So as we go down and fiddle around with the atoms out there, we're working with different laws and we expect to do something different, right? So I think what he meant, different things, perhaps at the moment he did not know exactly, but this is what we now know as quantum information science. And later in 81, about 20 years after, he gave a lecture on simulating physics with computers. So he mentioned the idea of using a quantum system to simulate another quantum system. Yeah, so this is some quote from that lecture. So he said, nature isn't classical, and if you want to make simulation of nature, you better make it quantum mechanical. It's a wonderful problem because it doesn't look so easy. So basically what he meant is that to simulate a quantum system using classical computer, it would take exponential number of time or time step. And therefore, it seems natural to use a well-controlled quantum system to simulate another. Okay, so that's what I said here. So he proposed to use something like a quantum simulator to simulate evolution of a system under some Hamiltonian. So I write in this time order integration because the Hamiltonian may have time dependent. Okay, so he proposed that we could study such dynamics, and this will be very difficult for classical computers. Okay, so these are very early idea from Feynman. So, and there also, long before that, there is development in classical computer, basically characterized by this so-called Church-Turing thesis, which was developed a long time ago. Okay, basically the essence of that thesis is as follows. Every function which would naturally be regarded as computable. So any function that can be computed by universal Turing machine. So if they can be computed in principle, there is always possible on a Turing machine. So, okay, maybe more colloquially, this means that universal Turing machine can be used to simulate any other classical computer. So at that moment, the computational model is purely mathematical. There's no regard to any physical system. So I simply said this is classical computer because the laws that these computer would satisfy or obey are from classical mechanics. Okay. I think we mentioned the Turing machine a long time ago, but this is a picture taken from Nielsen and Tron's figure 3.1. Basically, you have a long tape, assuming it could be infinite, and on each tape there's a memory cells. In each cell there's some state, and there is a header that goes along and read the state and can process that maybe by computing something and decided whether it's moved to the next or stay or move backward. It can also change the state of the memory cell. So this is the sort of fundamental picture of a computer. So this is called Turing machine. So essentially, the classical Church-Turing thesis says that any computable function, can be done efficiently on this Turing machine. Okay, I think I shouldn't use the word efficient because it may also imply the complexity. So I don't mean that. So, but in more plain words, the Church-Turing thesis says that even though this is a Turing machine could be quite old, maybe it's like 30 years old. Apple first generation desktop can in principle be used to simulate the task that we do on, for example, an iPad or Mac machine or Surface Pro, etc. Yeah, but of course, such efficiency would be very different because it would take a long time to finish a task, but such simulation is only polynomially overhead. So maybe it would take some polynomial n for a 30-year-old computer to simulate current classical computer. Yeah, but even for that same complexity, we will feel some difference. Okay, but the essential idea of this Church-Turing thesis is simulability by this universal machine. Okay, so why do I want to mention this? because there is a subsequent idea of quantum simulation, which was investigated by David Deutsch. He was thinking that could the law of physics be used to derive a stronger version of this Church-Turing thesis? If you need to take into account a physical law, would that change the picture? So he basically proposed the idea of universal quantum computer or a universal Turing machine, which is sufficient to efficiently simulate an arbitrary, finite realizable physical system. So he basically says that if we want to take physical law into the picture, the most fundamental one is quantum mechanics rather than classical physics. So therefore, I should consider a machine which is composed of objects that behave quantum mechanically. So this is also along the idea of Feynman. And his principle, or his conjecture or thesis is to claim that any quantum system or any physical system, okay, finite system, can be efficiently simulated on such a universal quantum computer. Okay, so that's what he proposed. Of course, this may not be correct because if we use physical law, we use quantum mechanics, but there are other physical principle or theory like string theory or quantum gravity, which may have a different power. So if you suppose that will be the case, then it might not be efficient to use a quantum mechanical computer to simulate a string theory or a quantum gravity. But at the moment, we don't know that. Okay. So therefore it's not a theorem. It's only a principle. And subsequently, about 10 years later, Lloyd showed that Feynman's conjecture is correct. So in the sense that quantum computer can be programmed to simulate any local quantum system. So I think by quantum system, he does not mean string theory or quantum gravity, any typical quantum system, many-body system. So, but he only limited the interaction to involve only a finite few particle. Okay. So he showed that evolving in small time step combined can allow us to perform efficient simulation of time evolution. And the overall time that's needed only grow polynomially with the size of the system. Okay. So this, yeah. So by evolving in small time step, this is what I meant. So imagine your Hamiltonian H is composed of many terms, the sum over H1 to HL. If you want to simulate evolution in time, you can do something called charter decomposition, and you make the time step to be small, and you raise to the nth power, and this is a correction, the first dominant correction, and that's the higher order. Yeah, so I'm going to talk about this more in detail next. Okay. So basically, if you have operation associated with Hamiltonian, so for example, if you are able to perform the time evolution of H1 tilde, H2 tilde, HL tilde, then any unitary evolution that can be similar of this form, e to the I a times t, and a is in the algebra generated by S. So basically what that means is you take any of the terms. So A can be any of these or summation of these, any time, so that you can simulate. You just write this. So that's called algebra. Okay. The algebra generated by this. So yeah. So this is mathematics, but let's look at the one that's specific, point to the Hamiltonian we discussed and this expansion. So by this small time step and running a few times, right? So he divided this time t into n steps, right? So therefore each step will be a small time. And then he raised to n. So he used an interesting analogy of parking a car. Yeah, suppose you want to park a car to some space, right? This is the space. And this is your car. And you want to park this parallel parking to this space. And you will do some forward and backward of sufficiently small distance and repeating many times. And it is possible to park into a tiny space. So that's the analogy that he used. And we can make this study more quantitatively. Okay, just to point out, this is the dominant area. And these are the high order term. Okay. So we can compare the simulations between quantum and classical. So let's first just look at classical system. If you have n qubit, the vector you need to simulate the wave function will be 0, 0, 0, for example, 0, 0, 1. This is the component, okay? And some coefficient, right, up to 1, 1, 1. So they are 2 to the n q component, okay? And the matrix, if you have e to the minus I ht, or sometimes people just slaply write a plus sign. This is a matrix of 2 to the nq by 2 to the nq, okay? And this is exponential in this number of qubits, and to multiply this u to that, it also is require exponential time complexity for a classical system. Okay, because you need to take a really big matrix and then apply to this component and sum it. And since there are 2 to the n times 2 to the n component, this require exponential time complexity. Okay, that's really just the hand waving estimation. But this shows that in general, simulating a many-body Hamiltonian is difficult. So in special situation, for example, the Hamiltonian H only involving a single particle, then it will be easy. So just suppose my Hamiltonian just involving, for example, just individual qubit with different B field, then this is simple because they don't interact. So the problem becomes complicated when you have interaction. Right? So for example, these two particles interact and those particles interact, etc. Okay, so let's do some analysis on our quantum simulations. So these are the Hamiltonian that we'll be using. So assuming there are L terms, and assuming each Hj, as I illustrated here, so maybe there should be a picture, yeah, that it involving maybe nearest neighbor, or maybe a a few small region, like each turn is really of small number of qubit interaction. Okay, suppose this is maybe 3, that will be 2 to the 3, that will be 8, assuming the dimension is n, this local dimension. And the number of operations to simulate this, okay, because this is like n by n matrix. Yeah, so the number of operations, if you want to decompose and get such a matrix using, for example, gate decomposition or other method, it requires order m square operations. Okay. And we can estimate because we're going to use, for each turn, we will do it n time, right? And there are L such turn, so the total number of operation, if assuming you are doing that sequentially, this will be L times n times m squared. Any question? Okay. So if you said you want the desired error to be epsilon or smaller, then the error, this is the accumulated total error. So then the error in each operation that you allowed, for example, any of these terms, need to be smaller than epsilon times total number of operation. Okay. Yeah, so as I said, we consider the L, we consider the interaction is only, for example, nearest neighbor or next nearest neighbor. And the number of these L terms is roughly proportional to NQ. For example, you only consider nearest neighbor, right? So that's the number of edges. So for example, number of edges. And still proportional to the number of total qubit. And for this expansion, right, because the error scale as t squared over 2n, and therefore because we require, suppose we require the error to be epsilon. So suppose this is the total number of error, we want that to be of epsilon, so the n will scale as t squared over epsilon. Okay, for time duration t, suppose we want to evolve a duration t, but for each operation, this is t over n, and t over n is t over this expression. It's basically 1 over t, okay? So the total number of time complexity is simply just proportional t, okay? So even though this is t squared over epsilon.
Why t squared?
Oh, this here?
Yeah, why it is t squared?
Suppose this is roughly epsilon. Yeah, because you are doing the first order expansion, the error is second order. Okay, so basically here says the time complexity is still linear in time. Yeah, and the dependence on the number of qubit would be small. I guess if you want to include this coefficient, suppose you want to include this coefficient, this will be as most n nq square, for example. So the time complexity is linear in t. So let me just say linear in t, but for polynomial, at most polynomial. In number of qubit. So therefore it's efficient in this sense, as long as it does not scale exponentially. Okay. So yeah, I'm using the argument from Lloyd's paper. This is this paper here. Okay.
So H is just the sum of HI.
Yeah, so H, total H, sum of these Hj from 1 to L. Okay, they're L term. So for example, you're talking about two-dimensional spin. This is one example. For example, this could be Heisenberg interaction, like this, okay? Example, okay?
So except for string gravity, are there something like a spin system that cannot be good approximated by this?
For a string system?
I mean, spin system,
Spin system, yeah.
are there some it cannot be?
Well, I mean, here we sort of limit ourselves to nearest neighbor. They could be long range. They can be long range spin system.
Like superconducting?
So, no, that's not superconducting. So, for example, if you have long range dipole interaction, but there may be other method to deal with that system.
Okay, thanks.
Okay.
I have a
But
question.
here we're limited to these Hj acting on nearby few spins. Yes, there are.
I think here it's unfair for this classical simulation because in quantum simulation you only consider a special case, but for classical simulation you consider the whole all the possible Hamiltonians. If you consider this subclass of Hamiltonians, then maybe this big matrix is only very sparse, so the computation should not be very high.
So yeah, okay, thanks for mentioning that. So in order to do the time evolution, right, you need to, let's say, the Hamiltonian, suppose you could classically diagonalize that. Let's say, let me just using this Nj, right? Suppose I have this. So the time evolution will be just in this lambda j. This will be evolution of time evolution. The unitary, sorry, the u of t is going to be this. Okay, this too small space. Sum over j. Okay, suppose you can diagonalize the system, then you can write down the evolution operator, right? Diagonal in the eigenbasis, right? So the problem is you need to get these lambdas, you will need to have order 2 to the 3 n cube complexity to diagonalize that. So it will be also difficult. Yeah. Even for sparse matrix, I think this will be the complexity. In general, if you only want to know the lowest eigenvalues, then if the matrix is sparse, then you can reduce this 2 to the 2n. Okay, but it's still exponential. Okay, unless of course, as I said, if this h is simple like this, it's really just independent n-qubit spin, then this is a simple problem because the problem basically factorized. Okay, does that answer your question? Okay, I hope that's yes. So basically, Lloyd's argument is that if you have reasonable Hamiltonian, to simulate the evolution is simple if you use one quantum system to simulate another. Okay. But in general, classical system is to simulate the evolution is very difficult. Okay. So I mentioned here, in some sense, we can let the system evolve in time, right? Individually, we may evolve a small time, right, using the individual Hamiltonian. But you could also use, if you have a quantum computer, then in universal quantum computer, you could really treat them as quantum gates. So just decompose these into a sequence of gate. Okay, and I think the time complexity would be similar because each may just incur some constant overhead. So you could also use, we call this digital because you're using a quantum computer. You're not using something that evolved under Hamiltonian. Okay, so this is digital versus analog. What I mentioned earlier is analog. This is allow evolution. Okay, something like that. Okay. Basically, what you do is just create a system, engineer the interaction, and let the system evolve. Okay. So that's probably the most simple way. If you really can engineer the precise interaction, you just turn on the interaction for the system to evolve. And that's probably the most simple way to simulate a quantum system. Of course, you need to be aware of the error. Okay. Okay, so we mentioned to construct qubit, we mentioned DiVincenzo's criteria, but there are also some corresponding criteria for quantum simulation. This was proposed or summarized by Cirac and Zoller in 2012. So let me just summarize what they mentioned in that paper. So first, of course, you need to have a quantum system. In general, this is composed of bosons or fermions or both. It could be a mixture of bosons and fermions as well. And they can have spins. They can also be of the same spin. So we would say spinless. And in order to do large scale quantum simulation, they need to contain large number of degree of freedom for the whole system. And ideally, we like to confine the particle in some region of space so I can apply some lasers or a magnetic field, etc. Okay, so that's the first requirement. Just like in qubit, we need to have a well-defined two-level system. And just as in the qubit case, we need to be able to initialize the qubit in, for example, 0 state. In this quantum simulation, we also need to be able to prepare the system to an unknown quantum state. It could be approximately. And the third criteria is Hamiltonian engineering. So we need to be able to engineer interaction. So for example, this could be a spin interacting with its neighbor, right? So we need to be able to this, and the strengths ideally could be tuned. So we should be able to engineer a set of interactions. It could also be maybe other, you could also have an external field. Maybe you could also have external field acting on some spin, some direction. Yeah. If you want to simulate open system, you may need to have reservoir. Okay. And they stress that among the accessible Hamiltonian, there should be some that cannot be efficiently simulated, at least for the current classical computers. Okay. So this is the third criteria. The next is, so once you initialize, right, and you have Hamiltonian engineering, you could let them evolve, right? And once evolve for your desired duration, you want to perform measurement. So that's the criterion for detection. You should be able to perform measurement, for example, on the individual spins or atoms, or maybe a few particular sites. It could also be a collective, maybe many particles at once. So it says ideally one should be able to perform single shot experiment, and that can be repeated many times. So for example, you have a system composed of interactions of these spins. So let me just write Heisenberg term just for example. I want to be able to just take a snapshot and to see if this is up or down, or could be in the different bases. Okay, something like that. Okay, this example. And I should be able to repeat such measurement many times. And we want to determine not just the expectation value of this observable, but also their function, the function of that, and then average over different instances. Okay. Yeah, for some system, this may not be that easy. In the past, for cold atoms, it's not easy to address in individual atom, but with recent development, this is actually possible. Okay, so that's the from 1 to 5 mostly about the physical system. And once you're done with your simulations, of course you want to be able to verify, right? But by definition, if we want to verify using our classical prediction, in general, this is not possible, right? So by definition, no, we have no way of verifying the result if the simulation cannot be classically simulated efficiently, right? This is for, let me say, this is for large, sufficiently large systems, right? But at least there should be a way that we can sort of know the confidence of our simulation results. So there are a few different ways. So first, it could be that among your capability, you were able to simulate some exactly subbable model. For example, like this Heisenberg model in one dimension is exactly subbable in the sense that at some special point, this is classically computable. So we can sort of perform the experiment at these special point, maybe the coupling or external field, and see if it sort of match as we scale the system size. Then we would be confident that the system, when simulated at coupling nearby, may not be exactly this, just maybe differ a little bit. Then we can trust the result. Okay, so that's one. Another maybe is that if we just limit it to simulate small size, we can solve by our classical computer. And as long as the scaling is sort of accurate as we perform the classical simulation compared to the quantum simulation, they agree within our classical computer capability, then we would be confident that when we scale it up, then it would perform well. But of course, there's no guarantee. There's other ways to do the verification. So since we're mostly interested in evolution, maybe we run it forward and then backward, and to see if it end up in the initial state that we start with. Okay. Or if we have different systems, different method of quantum simulation, we can compare with one another. Of course, this is not a complete list. There might be other new methods. Okay, but these are the 5 criteria. So let me just repeat. First, quantum system. Second, you need to initialize into some known quantum state, and you should be able to engineer the interaction, external field, and be able to perform ideally single shot. And then you develop some methods for verification. Okay. Yeah, let me maybe pause to see if you have any question.
What do you mean by engineering?
Yeah, engineering. So it could be, I would give some example. For example, you have atoms that it's in a double well potential, or maybe lattice, and they would tunnel. So there will be some tunneling rate, T, and there's also interaction, U. Yeah, so this is what I mean by engineering. And you could also apply external field. For some scenario, it might be possible to have some ring exchange interaction. So you might be able to have such kind of interaction. This may occur if you do some perturbation. Okay, so there are many ways to do that. I'm just giving you one example. Okay.
Does step 3 mean?
Can you speak louder?
Yeah. Does step 3 mean that you need to be able to simulate any interaction, or just the interaction that's relevant to your?
Yeah. So relevant
to
your problem of your interest.
Okay.
So I want to say that these quantum simulators, they need not be able to simulate all the system. Maybe one physical system can simulate such. Maybe let's say a trap ion can access such regime, and maybe other co-atom, or maybe other system. Yeah. So it's like that they can do different experiment to probe different regime, but hopefully there should be some overlapping regime. So then therefore one system can compare with the other.
Okay, thanks.
Dr. Wei?
Yeah. Yes.
I do not agree with you that you say the quantum gates, they are digital, they are not analog.
Okay, so what I mean is quantum computer, right? We talk about the gate.
Yeah.
Yeah. By digital, I mean the gate picture. Yeah. By analog, I mean the time evolution picture.
Yeah. So I think currently for example, the S gate, so we will turn on the interaction for a specific time.
Yeah.
So if the time is not accurate, we will get the phase maybe overshoot or not. So that is analog, because
okay. So yeah, that's a good point. So the construction of gate, of quantum gate, can be analog. But the operation from user's point of view is analog, is digital. Like for example, these are the finite set of gate that provided, for example, on the IBM. Of course, some phase gate you have some ability to do this such gate. Okay, but in terms of gate set, it's still discrete, of course. You say, okay, there's some continuous range, but in terms of universal set of gates. Okay. Yeah, so it's this is what I'm saying is this is the sort of the convention in the literature. We would say when you use quantum computer and you discretize the time step and decompose into gates, these are the digital quantum simulation. But if you are able to let the system evolve under some Hamiltonian, then this usually is regarded as analog. Okay. And usually the analog simulator, they are less susceptible to noise. So for example, you're doing experiment on some cold atoms, you may lose a few atoms, you may apply the field not precisely, but they can still be used to simulate accurately the phase diagram. Okay, actually this is what I'm going to show you, just a few examples. It's not a complete selections. It's probably not possible to do that. I just choose a few exemplary ones. For example, you might be able to use ultracold quantum gas. Okay, and such system provide high degree of controllability because they can control the interaction strength. They have novel detection scheme. For example, they have these atomic microscope you can use to image individual atom. Okay, and this is cleaner than solid state system because in solid state system it's very noisy because you have impurities, you have phonon, you have all sorts of different dirt, you have oxygen, oxides, and so. But the cold atom, ultra cold quantum gases are very clean. Okay, yeah. So more detail. For example, there's something called Feshbach resonances, can be used to tune interaction between atoms. So maybe I want to point you to Professor Schnabel's lab, ultra cold quantum system lab. I think I just misspell ultra. Let me just correct that. Yeah, so this system allow you to apply the magnetic field, and then you can have the so-called Feshbach resonances. So I don't want to discuss the detail of these Feshbach resonances, and they are used commonly as a tool. If you're working in the field or you plan to do that, then you can dig more into the detail. And they can be used to control the landscape. For example, they can trap, right? They can change the height, or they can change the spacing, etc. They can trap atoms in optical lattices. And the single particle energy will be very different, right, as you change this. So, and they can control that precisely. And yeah, so with the microscope, they can also detect single atom. Okay. Yeah. And more recently, you could actually introduce the so-called artificial gauge field, and that allow you to simulate. So simulate gauge field. Okay, so maybe for those who don't know the gauge field, you can think electromagnetic wave. And even though the cold atom is neutral, right? When we talk about a charge interacting with electric field, magnetic field, they can sort of introduce or engineer these artificial gauge field or artificial B and E, even though it's neutral, can simulate charge particle. Okay, so what I mean is that in your electromagnetism class, you learn about a charge electron interact with the electric field, interact with the magnetic field, etc. Right? So these they can sort of engineer that kind of artificial field. Okay, so that was more recent development that opens up a lot of possibilities. Yeah. So here I'm giving you an example. This is a paper by Greiner at collaborator. So what they did is they take a system of trapped rubidium atoms on a two-dimensional lattice, and they observe some phase transition from superfluid. So superfluid basically means that this is both Einstein condensation. And to Mott insulator, meaning that these are isolated, uncorrelated atoms. And if you're a physicist, this is described by the Hamiltonian. T is the hopping. You hop from one side to the other. U is the interaction on site. Mu is the chemical potential. It's not important to know each of these, but the picture is as follows. If you are a superfluid, because it's really coherent, and this is the image that they take after the expansion, they take this, and this has one peak that signifies that this is in a BEC. And as they change, for example, let me just illustrate, it might be changing the tunneling strength, and this can be achieved by lowering the depth of the trap potential, right? If you lower the depth, then it's easy to tunnel. So if they do that, they see that the peak, there's some auxiliary peaks, side peaks. At a certain point, there's no coherence. There's no sharp peaks. That means these atoms are sort of located at individual side. They are not related to each other. This is called Mott insulator. Yeah. So basically, this system simulates such a Hamiltonian. Like this looks like an artificial Hamiltonian, but it's precisely and accurately simulated by a system of trapped atoms. Okay, so that's one example. Okay, there are also others. I'm giving you really collections of experiments, and if you're interested, you can dig into more detail. This is the original paper. This one is more recent. It's used to simulate also electrons hopping on a conical or hexagonal lattice. Okay, and these arrows indicate the hopping. The hopping usually is annihilation operator and then creation operator at the other side. T is the tunneling. And in addition to a nearest neighbor, there's also next nearest neighbor hopping. And you can also apply a flux to change this, to give some phase to the tunneling. And there's also the offset of A and B energy. So maybe it's more energetically favorable to have atom located at B side rather than A side. Okay, so such model was proposed by Haldane, and that's what he got Nobel Prize for, one of the work, as he predicted that there is very distinct phases as you change these parameters. So for example, the phi and the offset energy, they are two regions, these called topological phases, as opposed to non-topological phases. And these are related to some mathematical object that define that topology. Yeah, I won't be able to talk into detail, but so you can see that these co-atoms can be used to simulate a model which constructs theoretically. It's very difficult to realize in the conventional solid-state system. But in co-atom, there's a really high degree of controllability that they can simulate such a model. Okay. Yeah. And maybe more familiar is our model of spin, right? So spin system, this is, for example, a magnetic field applied to individual spins. And these may have interactions. So in a group of physicists at Harvard, that they were able to trap these atoms, and they have 51 such atoms in a one-dimensional line. So you show that the schematic way, and they can simulate the evolution. So evolve certain time and then detect the final state. Okay. So they can use trap atoms to simulate really spin system with long-range interaction. So this indicated the interaction. Okay, and these are the energy level diagram. Yeah. So that's one example. There are more. For example, in addition to the co-atoms, so we mentioned earlier, you could also use trap ions, and these can also be accurately controlled, and interaction can also be engineered. And you could also, in this particular example, you can measure individual ions with almost 100% efficiency. So yeah, so here is a schematic of the system. You have, for example, pole trap, and use potential to trap these ions, and these ions repel each other, so they form one-dimensional chain. Okay, these are the detail level diagram. So let me not go into that. We mentioned these earlier in our lectures. Yeah, so something that has been achieved is to create some highly entangled states. This is from Block's group. You can check out the reference. So they create G at Z state. So we mentioned the G at Z state, right? So when we mention it's a 3-qubit. This is a 3-qubit example. And so they were able to create such kind of state up to 14 qubit. So these will be highly correlated state. Okay, and they can study the property of these highly entangled states. And for example, these are the phase of the analyzing pulse, and they look at the circle parity, and they see there's some oscillation. So the better quality of the oscillation indicate the better coherence and stability. So they were able to study these as a function of these noise. Yeah. So this shows that you can engineer this using, I believe these are sort of digital simulation to create such highly entangled states. Okay. Yeah, so there are also other example. This is beyond the so-called Paul trap. This is called Henning trap, and they trap in two-dimensional system. And in this particular paper, they demonstrate a variable range Ising type interaction. So this is called Ising type. So sigma z interaction. And these are long range interaction. And this is, they say this are naturally occurring two-dimensional triangular crystal lattice of hundreds of spin half particle. Yeah. So I think this is quite amazing because you can trap such large number of ions and then study the dynamics that's represented by such Ising interaction.
Is it
Okay,
doing
so you,
better?
yeah.
Is it doing better than classical simulations?
Of course, these are quantum mechanical systems, right? So this is, in some sense, this is commuting, so like classical, but you also have a field which is perpendicular. So for such large number, 300 ions, such model cannot be solved by a classical computer. For classical computer, you probably are limited to spins of fewer than 30 qubit, fewer than 30 ions. So with a large scale like this, it cannot be done classically.
So the Ising model is also 300.
Yeah, 300
spins.
Yeah, 300. Yeah, there's 300 ions. Each ion representing a spin, as you see schematic here. And this Ising model is not just nearest neighbor, but it's long range. So it can be here interacting with there. And so, yeah.
That's just a dipole interaction.
Yeah, so this is emerged, I think, from the dipole.
So we cannot
Dipole.
turn the parameter.
You cannot, what, say that again?
We cannot turn the parameter.
So yeah, so here the interaction depends on where the distance, most likely. The only thing that you can tune precisely is the external field. Yeah, even with such a limited tunability, it's always not already non-trivial. It's also possible you can change the trap potential. So maybe you could enlarge, right? Enlarge the system, so the atoms are more sparse, right? So that would change this Ij also. Okay, so here you see how you engineer, right? You apply external field, or you could change the spacing. That would change this coupling. Okay. I think, yeah, one of the most recent one, and it's very impressive experiment, was done in Chris Monroe's group. So what they did is that they have a 53 qubit quantum simulator as in one-dimensional chain, so as illustrated here. So these are, what they did is they initialize the spin in this particular product parallel configuration, and there was no interaction. Then they turn on the interaction, and these are also long range Ising-like interaction, and then they really let it evolve. And then they measure by looking at individual spins and see how the magnetization behave as a function of time. So for each time instance, you have to perform the measurement and then detect. For each point, let me just say, for each point is a one experiment. If you want to simulate this point, you have to evolve and then measure. If you want to simulate the next time, you have to do this. Yeah, it's not, you can do continuously, because once you measure, you would destroy the system or collapse the system. Okay, so this is their setup, and this is their measurement. Shown here, there are 53. These representing your single individual spin measurement. The bright spot could indicate it's state 1, the dark spot may be indicating state 0, etc. Yeah, so this is what they say. They use the quantum simulator composer up to 53 qubit. If you count, there should be 50 spins here. 53 to study non-equilibrium dynamics. So in the transverse field. So you see that this model comes up very often. So this also has long range interaction. And yeah, they observe some phase transition. Okay, but for detail, I would refer you to this paper. Okay. Yeah, and more interestingly, this group did something quite interesting. They demonstrate something called time crystal. Yeah, time crystal is really new sort of phase of matter. So basically, you have crystal that in space, meaning that the atoms somehow spontaneously become localized and collectively, right? Like the crystal structure. But it was also studied theoretically whether in time you could have such periodic pattern. Okay. And so it was proposed that this could appear in system with some random interaction, random coupling or random field. So the system is really good for that, because these interaction in some sense is long range, is random, and you could also apply some random field. So what they did is that they engineer their evolution for 3 different time interval. So for first time interval, they apply such Hamiltonian. So in a sense, they engineer so that the Hamiltonian is like this. They let it evolve for T1. In the second segment, they really just allow this Ising interaction to evolve. And then in the third segment, they just have the external field in the x direction. The beginning here is y direction. And then repeat this. So this is called discrete because this is one cycle. It's this. This is one cycle. And they repeat this for many cycles. And then they also record the response of their atom, the ion's magnetization. So you can see this is a function of time. And so when they do the Fourier transformation, they see that the frequency is 0.5 times 1 over the period. So this means that the response of the system somehow is lagged and appear only a period of twice, right? So you apply your system like this, and your response is slower. It's twice slower. Yeah, so this is what it's called discrete time crystal in this context, because the time evolution is in discrete segments, and response is not obeying the discrete time, one period, but actually is twice period. So this sort of break the symmetry, translation symmetry. And this is called time crystal. So this was, yes?
So the time crystal is just a complex version of resonance.
This is not really resonance. It's the response. This is dynamic response of the system. Yeah, so this This is not related to resonance. Yeah, so this was done in these ytterbium ions in this same group as previous slide. And this was also observed in this NV center diamond in Harvard's group. So they observed something similar. So they also do some discrete time sequence and repeat that. Sorry. And the way they do it is they really apply, for example, these wave to do the rotation microwave and to engineer the Hamiltonian. So let me not go into detail, but the upshot is similar. If they measure the response, and in a sense, they also get the response is twice the period. Okay. Yeah, so there are also other physical systems. We already saw the MB center and diamond, and we already talked a lot about the superconducting qubit. And mostly we discussed these in a sense of universal quantum computer. Okay, we also saw the limitation because of noise. So in order to use quantum computer for quantum simulator, you have to also be able to be robust against noise. Okay, there's also possible way of using quantum annihilers, for example, as in D-wave system. There's also the photonic system that I mentioned earlier. There are more examples. Let me see how much time we have. We have, okay, a few more minutes. This is one that using the superconducting qubit. So yeah, so I was saying that they were regarded as the gay version or disco version. So here they have 9 qubit. So see, they have 9 qubit, and they say that their qubit. This is in a group of Google. They say that their qubit is can be thought of as a nonlinear photonic resonator in a microwave regime, and this is the Hamiltonian. Yeah, you may recall that I showed earlier the Bose-Hubbard model. This is really the Bose-Hubbard model. Okay, we saw earlier in the core atom case, and they could change these so-called commutative potential to something of particular form cosine 2 pi n times b. B is essentially is the flux, and this is called Hubbard Hamiltonian. And if you plot the energy spectrum as a function of the flux or B field, you see this pattern. Nice pattern is called Hofstadter butterfly. So they were able to demonstrate such a pattern nicely here. Okay, so this is superconducting qubit. As for the photonic, there are a few applications. Something that I didn't mention is for photonic system. It's just as an aside, mostly people were study the so-called boson sampling problem. These are problems shown to be difficult for classical computer, but photonic systems are natural for this. But I did not have time to talk more detail on this. Could be used as an extended study that if you interested, you can study this yourself. But the photonic system actually was one of the earliest one to simulate quantum chemistry. So we mentioned we can do this quantum chemistry calculation on Qiskit. And the photonic system are actually the first, one of the first to realize this for hydrogen molecule. Yeah, so these are the detailed setup. If you're interested, you can also check out the paper. So I guess that that's close to the end. Maybe I will not move on to the next. So maybe Wednesday we come back and we discuss different subject, namely the quantum metrology and quantum sensing. So let me pause here to see if you have any question.
So you can engineer systems that don't exist. We don't know that exists in the nature.
Yeah, that's correct. So most of the time, theoretical physicists come up with some model, and then if you were an experimentalist and maybe you work on solid state, you will try to find material that would behave similarly according to the interaction, but you may not get exactly the same interaction strength and maybe even the structure, lattice structure are different. But in core atom is so versatile that you could engineer these interactions and have well control. So it may also be the case that the theoretical model have really complicated interaction as quite difficult to engineer. For example, something like this, if I have sigma z, for example, in these honeycomb toric, if I have 6 product of 6 interaction, it's very difficult. Even for experimentalists, it may not be easy. But it might occur in some regime of perturbation under the perturbation limit. Yeah, so this is really a research field, how you can use your system, not only cold atom, trapped ions, maybe superconducting qubits, or other system to study models that may not occur naturally. And you will learn a lot of maybe the phase diagram, physical property, even the time crystal, right? So time crystal did not occur naturally, but they could engineer this and verify this such existence. Okay. Any other question? Yes.
The simulations here are all digital, right? Like,
so here, in this, for example, time crystal. So using my definition, it's analog in these time period, right? They just let it evolve. They didn't use gate. They just have the Hamiltonian, let it evolve. But the discrete comes in terms of the cycle. So you have a total T1 plus T2 plus T3 as one unit, and you repeat that. You basically repeat that pattern, right? This is indicated here, right? So let me just make this bigger. So you have H1 and let it evolve, H2 evolve, H3 evolve, and then repeat, right? You do such repetition and observe how your system respond to such a periodic drive. I didn't wanted to introduce the name, but maybe I can say now this is called Fouquet system. So that's basically periodic drive. Yeah. So most these that I introduced here are analog. For example, this one is also analog, right? You really turn on your interaction, right? So you prepare this and then turn on the interaction and see how it evolves. And for quantum chemistry problem that we have seen, and these would be digital. This would be digital simulation because they were using gate-based method. So maybe digital, I would just say gate-based, okay?
Okay, thanks.
Yeah, sure. Other question?
So in terms of the so in terms of the readout, digital, you kind of sort of read out the state of the qubit and compute the value. But for analog, you just what you measure is what you want, right? For the qubit.
So analog, it's possible to measure sort of total magnetization. It depends really on the system, okay? Or in core atom, you really just let it expand. You let the cloud expand. Expand the cloud, and then you observe the density. So you really count, you can count the number. If you don't use individual, then you would sort of measure by imaging. These would be sort of analog way of measuring. But there's some example, right? This you could really do a digital measurement. So this really doing, so the measurement here is digital or single shot. Let me just say single shot measurement. So they, in some sense, this experiment, they combine the digital, so analog evolution.
Plus the digital measurement.
And plus, yeah, digital single shot measurement. Yeah. So it depends on the system. You may combine different way of measurement. Ideally, we like to have single shot because then you can measure not just this. You could also measure some power, right?
Yeah.
So that would be really useful. You could also measure maybe correlation, etc. Okay.
Thank you.
I think we've used up time for today. So maybe I'll see you guys on Wednesday. I'll start recording and feel free to leave.